deplete the t squared down to a t, right? But to get rid of it completely, we'll have to do another iteration of integration by parts to get it down to a constant. I hope that makes sense. And that's why I put up here repeated integration by parts. This is an example where you have to do it more than once. All right, let's stick with this. I like it. So du is 2t dt. And v here, Shay, you want to tell me that?
Sine, or 1 over beta.
1 over beta.
Sine beta t.
Sine beta t. Everyone okay with that 1 over beta? That's your constant. You have to scale out that constant. Good thing we talked about that earlier today, yeah? All right. Let's go. Let's crank it. What's our, this integral becomes, how do you want me to write that?
T squared
Okay.
over beta.
Okay, you want me to go t squared over beta? I'm fine with that. Sine beta t?
Sine beta t.
Everyone cool with that? Yes? Okay, now what?
Minus the integration.
Okay, so I'm going to do something a little bit different here. I'm going to do minus. I'm going to leave a space there because I want you to pull the constants out right now. So what constants from voodoo, right? This is our voodoo. What constants, Shay, can come out? 2 and 1 over beta. Both of them come out, right? So I'm going to write out here 2 over beta. And what's still in there?
You still have 1 over beta sine, or sine.
1 over beta came out.
Yeah, sine beta t.
You have sine beta t. Also
2t. Or t.
t. So we still had the t, we still had the dt, and we still had the sine beta t. All those are still there, right? So I'm going to write that like this. T sine beta t dt. I'm going to just write it in that order because it looks best that way, right? And now it's almost like we start a whole new problem over. We look at this and say, oh, can we do this? And then you say, ah, yes, I can do it with integration by parts because if I let that be u and let that be dv, then I can kill off the t. Yes? So we go again. So remember, everything I'm going to do now, everything I do now is just here what's in this brackets. Right? I still have that minus 2 beta out front. Okay, so my new table that I'm going to do right here, it's okay to use the, u and v again. Okay, in this, you can use u and dv if you're doing integration by parts again. So now, let's move on to someone else. Priscilla? You understanding? Feel like you're getting it?
Yeah, somewhat.
Okay. So you're starting out with this problem, and we want to do integration by parts.
Right.
You're okay with recognizing that? Okay, so what do you want your u to be?
T.
T, okay, and that's because in the new integral, it's going to be, in the new integral, when we do the formula, that's going to become a 1 dt, or just a 1, right? Okay, and then dv will be?
Everything else.
Everything else.
Sine beta t.
Dt. And now we just go differentiate down, integrate up.
So d would be just dt.
dt.
And then that would be negative cosine. And then 1 over beta.
There we go. Everyone see that? Antiderivative of sine of something is negative cosine, but because this is linear inside, you got to scale by it. All right. Okay. Let's continue. Let's continue. So back up to this. We are equal to t squared over beta sine of beta t minus 2 over beta. And then this is where the bracket started. So that integral right here will be replaced with ultraviolet minus voodoo again, right? We have to do a new ultraviolet minus voodoo off of this table. So let's move on. James S. James Sykes. Okay. We are trying to rewrite this integral using our ultraviolet minus voodoo from that table.
Oh, right, so what I got was, it was going to be negative 1 over beta t
Negative 1 over beta t
cosine beta t
cosine beta t
minus
minus,
integral sine beta t.
I left a space there for you. Maybe I'm going too fast, but we have minus from the formula, right?
Right.
And then we're going to do in here voodoo, which is going to be these two multiplied, right?
Oh, yeah.
So any constants that you have on these two, you can pull out.
Yeah, I miswrote it. So it's going to be negative 1 over b on the outside.
Negative 1 over beta is going to come out.
Yep.
And then from this, there's nothing to pull out. It's just, okay, so when I pull that negative 1 over beta out, I'm going to put it right here like this. That will turn into a positive, all right?
And then on the inside of the integral, it's going to be cosine bt dt.
Cosine beta t dt, like that. And then close it off. Ultraviolet minus voodoo. Integral voodoo. It's a lot to keep track of, yes? All right. Now, can we actually find the antiderivative of this? Are we finally to a point where we know this antiderivative?
Yes.
Yes. What's the antiderivative of that right there?
Negative sign.
It's
Negative sign, or negative 1 over
1 over beta sine beta t, right? So the antiderivative cosine is just positive sign. So this part is what we're going to get from this, right? Now we still have this to worry about and all that and brackets and everything else, but I'm going to do that on the next line. I just wanted to kind of get ahead of ourselves and be like, okay, this we can do, right? So final answer time. Well, maybe not. I might have to clean it up a little bit, but let's see how this goes. All right, starting from here, this equals t squared over beta sine beta t minus, so do y'all want me to distribute right now? Do y'all want me to, I'm not going to distribute yet. This is our first example. So I'm going to leave that. Here's our bracket. I have minus 1 over beta
Can
t
we write that as t over b?
cosine of, can you rewrite what?
That as t over beta?
Where? Oh, this? Yeah, if you want to put that t up there, you can. It's just preference. Yeah, it's preference. Whatever you want. So we've got that, and we've got brackets, we got this, and then this became minus minus plus. So this is plus 1 over beta times this, right?
Yes.
So what's 1 over beta times 1 over beta sine beta t? 1 over beta squared. So plus 1 over beta squared sine beta t. And now we can close off the brackets, and then we can throw a constant on the end because we're done doing antiderivatives. Now it's just clean it up. Really, there's only one thing to do, and that's distribute this through. So our final answer will be that this equals t squared over beta sine beta t, okay, plus 2 over beta squared t cosine of beta t. That's just me distributing this to this. Negative, negative is positive. And then my last one will be minus 2 over beta cubed, right? And then sine beta t plus c. There it is. Questions? What do y'all think? Yeah, I get it. It's a lot, but I told you. I mean, this is the first. We're now getting into the real like integration. This is the part that makes things rough. So what if that was t cubed?
We'd have to take it.
You'd have to do it 3 times. Wouldn't that suck?
So if we
Yeah.
know that we have a squared right there, we know that it'd be repeated. Is that correct? Because we'd have to integrate
For
2
this
times.
particular form, yes. I mean, that's kind of.
All the space.
You know, if you have the variable to a power by itself next to a trig function, let's talk about that. If you had an integral, okay, and let's say here you had like x to the nth power, and right here, let's say you had, I don't know, either sine or cosine, doesn't matter, sine x, cosine x, then that should be an indication that you're going to be doing integration by parts a couple of times, right? Because every time you do integration by parts, the power on this comes down 1. And this just switches back and forth between sine and cosine as you integrate through the method, right? Okay. We won't check that one? I mean, I'd love to, we just don't have time. Let's do this one first before we do the next one, or the one that was originally before it. So the antiderivative of natural log x. Kim? Kim? Yes? All right, Kim. So when you look at that, you make sure there's no like basic U substitution or anything like that, right? We really have nothing but integration by parts, right? So what would you let U be? What would you let dv be? You got to choose something, right? The natural log of x, okay? And that means dv has to be dx. I mean, that's really the only choice we have. Would you agree? Okay, so let's go with that. So Kim, if we keep going, what's this one going to be? And then what's this one going to be? So what's this? Did I not put plus c? I had put it before. Maybe on the very last one I forgot to put plus c. Okay. So 1 over x, right, dx here. And then the antiderivative of dx would be, so this is really just like a 1, right? So x. That actually doesn't look too bad, does it?
No.
So we have that this is ultraviolet, these two multiplied, right? So I'm going to put the x in front of the natural log, just looks nicer that way. And then minus the integral of what? X times 1 over x, right? So what happens there? They go away, right? And you're just left with 1 dx. Do y'all see that? You'll see how this x and this 1 over x multiply and they're gone, and you just have dx there? So what do we have then for the antiderivative of 1? Didn't we just do that? The antiderivative of that's just x, right? So this is just x ln x minus x plus c. So that is the antiderivative of natural log of x. It's x ln x minus x. Now someone verify, I do not believe that's on your formula sheet. Can I use these real quick?
Yeah.
I do not think, on your formula sheets we have, there's a bunch of antiderivatives on here for you. So I might, take the weekend to, during Super Bowl maybe, you can just sit there and thumb through this. Natural log's not on here. I don't know why, it's weird.
Can we write it on there?
That's why I'm making sure, yeah, it's not on here. That's why I wanted to put it in the notes, because this one does come up quite a bit. So this is one time I'm telling you, you can go to your formula sheets and you can add this to your formula sheets. So here's the way I would write it on your formula sheet. So it's consistent with what's on there already. Put natural log of u du equals u times natural log u minus u plus c. Because in your formula sheets, they use u instead of x. So that's the way it should look on your formula sheet. should we check it? This one will be easy to check. I'm going to go up here and check this. I'm going to take derivative, and that's a product. So what's the derivative of this? It's 1 times ln x plus derivative of ln x is 1 over x times x, finishing product rule, and then minus derivative of x, which is 1, and then derivative constant 0. So you just get ln x plus 1 minus 1. So these go away, and you just get ln x. I have another one I want to do that's not up here. That's an 8. All right, G. Give you a moment to write that down and think. You know, I really wish we had time in a class like this where we could, like, I could do an example and then I could say, hey, now you work one, and you sit there and work one, and then we all talk about it. We don't. I have to show you as much as I possibly can because there's so many little things you need to see. You know, I hate just coming up here and just doing problem after problem, but that's kind of what we have to do in this class. There's not much of an option. Unless y'all wanted to be here for like 4 hours every day, but I don't think you want to. Okay, so who's going here? Salo. No, G, sorry, I called G. Yeah, I apologize. I apologize, G. G, what are you thinking? Okay, so here we're going. You want u to be the x to the 8th?
Yes.
And that forces you to have the dv be natural log x dx, yeah? Now just run through this in your mind, G. Will you be able to differentiate this? You can take derivative of that, right? Yeah. It'll get nicer too because the power will come down, won't it? Yes? Now you also have to integrate this. Can you integrate natural log of x? We just did, right? Yeah. So, but what was its antiderivative? Like x ln x minus x? That's pretty ugly. And then you have to do that times this one. Maybe we do it the other way around. So look, with the cosine, like if this was cosine, right? Then it actually, we would have to do this 8 times if it was cosine. But it's not cosine, but I gave it to you intentionally because I was hoping G would tell us to do this because this is not going to work. But if we flip it, it will. Let's see if we flip it, why it works. So if we do the natural log x here, and we do the x to the 8th dx here, so G, do you want to kind of explain why this way is going to work now?
Well, you won't have to do it like 8 times.
You won't have to do it 8 times because when you take derivative here, what do you get? 1 over x, right? dx. And now you're not dealing with any natural logs anymore, are you? And then when we integrate this up, yeah, the power's going to go up. Big deal. It's going to go up to what? You know, 1/9 x to the 9th?
Yes.
But see, when you do voodoo, that's nice, isn't it?
Yeah.
You know, what's 1 over x times x to the 9th, right? That's doable, right? We don't have any logs in there anymore. So it works out better this way. In fact, the other way I think would be really, really difficult. So let's write this out. G, I'm going to let you keep going here. G, are we good with what we've done here? Like, are you comfortable with this?
Yeah.
Okay, so go ahead, G. Tell me what ultraviolet minus voodoo is going to look like.
Natural log of x times 1 over 9.
Okay? I'm going to write it that way, if that's okay with you.
Minus
I'm going to leave space there for you.
1 over 9.
Okay?
Then x to the power of 9
Okay?
to the power of 9
Okay?
times 1 over x.
Okay? Don't forget dx. Okay. Yes? But this is really just going to turn into what? X to the 8th, right? And can we integrate x to the 8th? Yeah, sure. We already did it just a second ago, didn't we? So I'm actually going to just write x to the 8th now. And everyone hopefully understands where that came from. So we can now go 1/9 x to the 9th times natural log x minus 1/9 times 1/9 x to the 9th plus c. So ignore that, do the antiderivative of x to the 8th, you get 1/9 x to the 9th again, and then hit it with the negative 1/9, and you'll wind up getting a negative 1/81. You okay with that?
Could you make it a little bit cleaner by factoring the 1/9 out of the entire?
You could do a 1/9 out of everything, yeah. Now I would, is it cleaner? I mean, I think that's subjective, you know. It's still the same answer, so. Now if we were being asked to factor it or set it equal to 0 or something, we might want to do some algebra, but you know, it's just as well this way. Well, I would want to put those together. That I would do. So I would make this negative 1/81. Okay? All right. The rabbit out of the hat. So this is a classic problem, right? Every Cal 2 student needs to see this problem. So now Salo. Where's Salo at? Oh, you're right in front. Okay. E to the 2x times cosine x dx. Do you remember, Salo, what I told you Dr. Richardson was trying to beat into our brains? That this method is really just like a transferring of the derivative, right? So if there's two pieces in there, one of them is going to get differentiated, the other one's going to get integrated in the new integral, right? One of these gets differentiated, one gets integrated. So Salo, in your new integral, right? If you do integration by parts on this, in your new integral, if you differentiate this one, what's it going to be? Same thing, right? And if you integrate this one, it's going to be what? Sine, right? Let's not care about the constants, okay? Differentiate this, you're going to have basically itself, right? You integrate that, you're going to have a sine, which looks almost exactly like this, right? If you do it the other way around, you differentiate that one, you're going to get sine, right? And if you integrate that one, you're going to get e. So it seems like nothing gets better. Do y'all agree with that? That's what I'm trying to get you to see. Like in the previous problems, like either the t went, or like the x went away, or the t went from t squared down to t, then gone. With the natural log, we took derivative natural log, went to 1/x, so it kind of went away. Things got better, right? With this, do you all see that they both kind of suck because they never go away? Like e's just going to keep staying e, and cosine's either going to be sine or cosine. Yeah? So it may appear at first glance that nothing we do is going to work. But like I read out of that book a second ago, like sometimes you just have to try something. So just give me your first instinct, Salo. What do you want for u, and what do you want for dv? You want to do cosine x? Okay. And what do you want for dv? E to the 2x dx, right? Okay. So is that legitimate? Like, can we do that? Yes? All right. Let's go, Salo. You tell me what du is?
Sine x.
Negative sine x dx, right? Because you took derivative. And then now be careful here. You want the antiderivative up here. So antiderivative, same thing, but there's one other thing you have to include because of chain rule. 2, but it's 1/2. There you go, right? All right, so that's where we are. So let's take a look at the new integral. Equals ultraviolet. These two multiplied, right? These two multiplied. So I'm going to write that 1/2 e to the 2x times cosine of x minus the integral. I'm going to do this one really slow. Integral of 1/2 e to the 2x times negative sine x dx. I decided to not pull any constants out on this one because I'm just going to do it on the next line. Do you all agree that's ultraviolet minus voodoo integral? Okay, now I'll clean it. So this is equal to 1/2 e to the 2x cosine x. And when I pull the constants out, I should get a plus, right?
Yes.
Plus a half.
Yes.
Integral e to the 2x sine x dx. All right. Marissa, you're up. So what are you thinking here? This is our new integral, right? I mean, this is our answer to that is this. And you're looking at that integral. Any thoughts on that?
Another integration by parts.
Okay, but why? Why another integration by parts? I'm like,
That's all we can do.
because that's pretty much all you can do. I mean, this is, would you agree, Marissa, that this is really no better than the original problem? Do you all agree with that? Like nothing got better. And it doesn't seem like it's going to get better, right? It doesn't seem like it is. But we're gonna go. We're gonna do it. So now you have to be careful on this step, Marissa. You're gonna tell me what you want me to do here. And there is a wrong path here. So
Okay. I guess I'll do the same that so sin x is
good. Okay, you're going to do the same thing that he did, which is you want to let the sine x be here. So you're letting the trig one be here, and you're letting the exponential one be here. Now, let's discuss why this works, or is going to work, and why it would not make sense to put the e here and the sine here. You could do it, right? Like I could put the sine here and I could put the e here, but why wouldn't it work? Well, think about this. Over here, we did cosine and e, right? We differentiated, integrated. So if we put the e here and the sine here, we're going to differentiate and integrate. So we're actually going to like undo what we just did. We're going to take sine to where? Cosine, which is kind of like, that's where it came from, right? And we're going to take this e from here back. So keeping it, you know, he started with u's, right, Solid? Who did it? Solid? Solid messed us all up. No, I'm kidding, Solid. No, you had a choice. You made this choice. But by making this choice as a trig function for you, we're going to put the trig function here also. If Salo had done e to the 2x here, we would do e to the 2x here. All right, let's see what happens. All right, du, Marissa, cosine x dx, and v, 1/2 e to the 2x. All right. I'm going to rewrite everything now. And right now, this is, I'm working with this. That's what we see in this box, right? That's this integration by parts box, goes with that. All right. So here's where we're at. We are at that equals 1/2 e to the 2x cosine x. Then we have plus 1/2 brackets. Okay, go ahead, Marissa. What do we got?
Okay, 1/2 e to the 2x sin x
E to the 2x sine x. That's ultraviolet, right? That's these two multiplied.
minus 1/2 integral
And it's 1/2 integral
of e to the 2x cosine.
e to the 2x cosine x dx. That's your voodoo, right? Ultraviolet minus voodoo. So we did this times this minus the integral of this times this, and Marissa pulled the half out. Got this, yeah? Are we all there? Now what's wrong with that? Fernando? Where's Fernando? No, Fernando? Alex? Where's Al? Alex, do you see anything bad about what just happened? We just got back to the original integral. Didn't we?
Yeah.
Like we got this, and that's what we started at, right? It's not a bad thing though, okay? Here's why. Here's why. Just bear with me here. Follow this through. This is why it's a classic problem we have to show you. Okay, this is going to be 1/2 e to the 2x cosine x plus 1/4 e to the 2x sine x minus 1/4 integral e to the 2x cosine x dx. All I've done is gotten rid of the brackets, right? Just distributed through. Y'all agree that's where we are? Okay, so now we see the original integral here, and we're kind of like, what the hell? So I would like to rewrite everything now. I'd like to start with the original problem. And I'm going to rewrite all this. 1/2 e to the 2x cosine x plus 1/4 e to the 2x sine x minus 1/4 of these integrals e to the 2x. Because I heard, ooh, what was that about?
You gonna cancel?
They don't quite cancel, but they do something. Look, we have one. We want to know what this one apple is, right? We have one apple right here. And this apple is equal to all of this crap minus 1/4 of the apple. So what can I do algebraically to both sides of this equation? Add that integral to both sides. So come in here and say, add 1/4 of this apple to this side. That'll kill it on this side, won't it? And over here, when we add it to this one, what's one apple plus 1/4 of an apple? 5/4 of an apple. Do y'all see what I'm doing? Adding it to both sides. They go away here. And on the left side, you get 5/4 of the integral. Yeah? We're almost there. So we get 5/4 of the integral e to the 2x cosine x dx equals, now notice this side no longer has an integral in it, does it? Right? This doesn't have an integral anymore. Now, we're almost there. We didn't want 5/4 of this. We wanted what? 1. So how do we get rid of the 5/4? Divide, because this is multiplication there, right? So divide by 5/4 is the same as multiplying both sides by 4/5. Right? So multiply this side by 4/5. You'll get a 1 out here, and then just multiply this whole side by 4/5, right? And we'll distribute that through. So this will go to here. That'll give me what? 2/5? 2/5 e to the 2x cosine x plus here to here will give you 1/5 e to the 2x sine x. Right? We're not done. Plus c. Okay, so on this problem is a little weird because of what you do to both sides. You really kind of miss the plus c. But we know this is the antiderivative, so we know it belongs to a family. There's really no other integrals that behave this way. This is like a very special type. And the thing that kind of leads you to know that this is going to happen is the fact that both the e and the cosine both keep like switching back and forth. None of them get better. All right, what do y'all think? So we're not done. This time we still have 7 minutes. We're not done. We have a few more to do still, and we don't have enough time to do these today. So I would say you need to start this homework for 6.1. Do as much as you can. All right. There will be some problems that you can't do. I wanted to show you, I told you I was doing the differential equations stuff, right? Oops, dang it. So here was a problem. Oh, let me erase some of this stuff. You see what I'm talking about? Yeah, this problem is not supposed to make you be like, what the hell? I mean, you should look at that and not really know what you're looking at. It's a differential equation right here. We call these linear differential equations. So this is an example of one. And in the process of working this out, well, one thing you've got to do is you've got to be able to do the antiderivative of 2 over x. Okay, so that's part of the problem. So you need to be able to compute that integral. And then look at this part right here. See that? I just did an integration by parts on this right here, x e to the x. And see on my table, I don't label u and dv. That's because like after you do it enough, you don't even need it labeled anymore. You just do it. So there it is. And then I had to do a separate, different one, x natural log x. Okay. Let's see. This problem, I only had to, well, did I have to integrate anything else here? Oh, I had to do this integral right here, which looks terrible, but this is a basic u sub. That looks bad, but it's just a basic u sub. Hyperbolics. This one, another integral, basic u sub. Oh, here we go. Here's another one. Y squared e to the y. I had to integrate by parts twice. Okay. Keep track of everything, and then that answer just got thrown in here, and it's just part of a bigger problem, right? So I guess what I'm getting at is, you know, these methods do come up in later classes, and you're not going to sit there and spend, 20 minutes in class going, let's go over integration by parts. It's just like, you just do integration by parts, and you get to this answer. Right? So, okay. 6.1 homework. Quiz? 5 minutes. Okay, well, do y'all want to hold off on it? Yeah, we'll hold off on it.
Yes.
5 minutes is not enough time. Yeah, so quiz 3 will be definitely on Tuesday. All right.
Can we just have it?
And it'll, well,
Can we take it home?
yeah, I'll redo. Let me just put the problems up here. It'll be easier. Like I said, this was like a level 3. It was like a level 3 out of 10 quiz. It was only 2 problems. It was that one and this one. And that second one is actually a homework problem. So if you did your homework, you would have recognized. You just did that problem. Yes, I know. When you were doing it, I was like, oh, wow, he's going to remember that on the quiz. So that would have been the quiz problems. I probably, honestly, would have given you 8 minutes to finish it. So do those, don't do them right this second, but maybe go sit down with them, start your watch, and see if you could do those in 8 minutes without looking at your notes. If you can, then I think you're where you need to be. 10 minutes, okay, you're still within reason. If you're sitting there like scratching your head, you're not where you need to be. Yes?
We have been able to use our formula sheets
Formula sheets are allowed, yes.
on every quiz.
On everything, yes.
So we're going to have a different quiz Tuesday.
You'll have a different quiz on Tuesday, and it will include integration by parts. So I should tell you as you pack up here, your first test is scheduled for the 11th, I believe.
The 11th of February?
Yeah, I believe it's the 11th of February, yes. And that exam will stop at 6.1. So I can tell you right now that we are probably going to talk about 6.2 before you take the test. I'm thinking the day before the test we'll be talking about 6.2. But the test will stop at 6.1. Now the reason why I'm telling you that is because exam 1 is going to be the easiest exam that we take in here. And the reason is because you only have your basic things like, then you have your power rule, your U sub, and integration by parts. That's it. When you get to exam 2, everything's on the table. Everything we've done.
So everything from what we started in the class?
No, I give you an integral, and you have to be able to look at it and figure out of all the different things we've learned, how to do that integral. Like I'm not going to I don't give you an integral and say, use integration by parts to do this.
Right.
I don't prompt you. And that's because that's what makes this inherently difficult, is after you have all these methods,
Which method do you use?
I throw one at you and you're like, okay, what do I do? And if it takes you 20 minutes to figure out what to do with it, then that's bad. So this first test is an opportunity to really try and get a good grade. Okay, everyone, have a great weekend. Go Cowboys. Wait, who's playing this weekend?
Kansas City at San Francisco.
Okay, all right.
San Francisco's gonna win, just saying.
Oh, really? All right, okay. You sound very confident about that.